Next up, we're going to look at number 22, which is kind of similar to number 14, but we've got a different shape, but we are trying to minimize cost of material. So in this case, we're talking about a cylindrical can. So again, I'm not the greatest drawer, but I can handle this pretty well. And here's my cylindrical can. It doesn't have a top. It's made to contain V centimeters cubed of liquid. So we're not given a constant for the volume like we were in the previous question, an actual number like 10, but the volume is constant at V, whatever V is. So I'm just going to write down that the volume is V, and that's understood to be a constant. And you might ask yourself, why don't they just tell us the number? And the thing is that once we solve this, then we'll be able to answer the question for any volume V, basically. And so we'll be able to say, so if the volume was 5, or if the volume was 10, or if the volume was 20. And we will only have had to go through this process once. Okay, now we're trying to find the dimensions that will minimize the cost of the metal to make the can. So note to self, we were not given any cost of materials like we were in the previous question. The cost to make the base is this, the cost to make the sides is that. But minimizing cost of metal is equivalent to minimizing surface area. In other words, if I make the surface area as small as it can be, then the cost of the metal to make the can is going to be as small as it can be. So I need an equation for surface area, or a function. I guess I should say function. Okay, now I need to label my diagram with some dimensions. And so, for example, the radius of the base and the height are the two that are going to be important to me. So the surface area is the area of the base plus the area of the cylinder part. Now the area of the base is easy, that's a circle, and the area of a circle is pi r squared. Again, I've labeled my radius r. The area of the cylinder is actually the area of a rectangle. If you imagine, for example, a soup can, if you take the label off and unroll it, it will be in a rectangular shape. So the area of the base, again, is pi r squared. The area of the cylinder is a rectangle length times width area, where the width is actually h. The length is the circumference of the base. So again, if you picture a soup can with a label on it, if you unroll that label, so you've got a rectangle, then the length of that rectangle is actually the circumference, the distance around the outside of the can. And the width of that rectangle is the height of the can. So I have my function for surface area, and I want to minimize that, but again, it's in two variables. So how can I solve for either r in terms of h or h in terms of r? So surface area function is in two variables. Need to solve for either r or h in terms of the other variable. So in other words, I can solve for r in terms of h, or I can solve for h in terms of r. So I'm going to go back to the volume being V. That volume V is the area of the base, pi r squared, times the height. So, for example, here I could solve either for r or for h. Solving for r involves taking a square root, so I think it'll be a little simpler to solve for h, and that is the volume, whatever that constant is, over pi r squared. So again, keep in mind, even though we weren't told a number for the volume, we have a constraint on this can that it's got some constant volume that it can hold. Okay, so now my surface area function as a function of radius is pi r squared plus 2 pi r times this hv over pi r squared. And I can do, again, a little bit of simplifying here so that I have pi r squared plus 2v over r. Now, once again, in order to, in this case, I want to minimize. In order to minimize this surface area, I need to find critical points to look for a minimum. So I'm going to take my surface area function and find its derivative. The way I find critical points is I find where the derivative is either 0 or undefined. And so the derivative here is 2 pi r minus 2v over r squared. Now again, this can be confusing because we've got all these different letters in here. Pi, of course, is a number, it's a constant. R is a letter and v is a letter, but this surface area function is in terms of r, and so again the v, even though it's a letter, is understood to be constant. So we're taking the derivative with respect to r. Now remember that critical points are where the first derivative is 0 or undefined, but they have to be in the domain of the original function. So once again, r equals 0 is where the surface area derivative is undefined, but r equals 0 is not in the domain of the surface area function. Surface area function is undefined when r is 0, and as in the previous example, this situation doesn't really have a content. If r is 0, then there's no can, so we can't really work with that. So we should make a note that we're talking about positive radius only. So now I'm left with setting my derivative equal to 0. Whoops. So 2 pi r minus 2v over r squared I'm setting to 0, which means 2 pi r is equal to 2v over r squared. And I'm solving this for r. I get that r cubed is 2v over 2 pi, or v over pi. So r is the cube root of v over pi. So again, we don't actually have a number here, but imagine once we verify that this in fact is the location of a minimum and not a max or neither, we can substitute any value for the volume and we'll get the correct location of the minimum. So once again, I'm going to use the first derivative test. I'm going to set up a number line with this critical point on it, and I'm going to look at the derivative of surface area versus surface area. Now again, this is a little bit tricky because we don't have numbers we can plug in, but hopefully you can see, and using the previous example as a guide, that if my radius value is smaller than the cube root of volume over pi, then my surface area derivative will in fact be negative. And if I have a radius larger than the cube root of volume over pi, then my surface area derivative will be positive, which means my surface area function goes from decreasing to increasing. So once again, I have not only a relative but an absolute minimum when the radius is the cube root of volume over pi. Now, the question said, find the dimensions that will minimize the cost of metal to make the can. So always make sure that you go back and read the question and make sure you answer the question. The radius will be the cube root of whatever that volume is over pi, and that's of course in centimeters. Now the height is going to be, well, I should spell out height for this. It's my last hurrah here. Based on what we solved earlier, right, the height is volume over pi r squared. That is the volume over pi times the cube root of volume over pi squared. That's a mouthful, and this is also in centimeters. I'm just going to make that a little neater. It's a little bit sloppy. So basically, I had solved earlier in my constraint for height with respect to radius. So now I'm going to take that radius of the cube root of volume over pi and square it, and volume over pi times that cube root squared will give me the height dimension.